Good morning, students. In today's session, I will discuss Unit 2 Mean Value Theorems. The contents of mean value theorems are Rolle's theorem, Lagrange's mean value theorem, Cauchy's mean value theorem, Taylor's theorem with reminders, and Maclaurin's theorem. These are the 5 topics of mean value theorems. Now, contents: Rolle's theorem, geometric representation of Rolle's theorem, applications of Rolle's theorem. So here in this session we will discuss about the topics of Rolle's theorem. In that we will see the statement of Rolle's theorem, geometrical representation of Rolle's theorem, and applications of Rolle's theorem. The statement of Rolle's theorem. Let f from closed interval ab to R be a function. The domain of the function is closed interval a comma b, and the range of the function is real number set R. Such function satisfying 3 conditions. The first condition is f of x is continuous on closed interval ab. So here ab is the interval. In this interval f must and should be continuous. Continuous means f is well defined, and at every point of closed interval a comma b, the curve is well defined and having the diagram of curve with no breaks at all. So clearly this is the curve y is equal to f of x curve, no breaks at all. Such curve is a continuous curve. So f is continuous on closed interval ab, and f is derivable or differentiable on open interval ab. So differentiable means f of x must and should be differentiable in closed interval a comma b. That is, the derivative must and should be existed. So second condition is f of x must and should be differentiable in open interval a b. Third condition, f of a equal to f of b. That is, the functional values are must and should be coincide at the end points. The end points are a and b. That is, f of a is equal to f of b. So f of a must and should be f of b. Then there exists at least one value of x in open interval a comma b. Call it as c such that f dash of c equal to 0. So whenever the function f satisfying these 3 conditions, then there exists a value for x in between closed interval a comma b, that is open interval a comma b. Let it be the value be some c such that f dash of c must and should be 0. So here x value is, let it be some c, which is satisfying the equation f dash of c is equal to 0. So it is the statement of Rolle's theorem. So Rolle's theorem is important for 2 marks. Statement is f is a function defined on closed interval ab to R such that satisfying these 3 conditions, f is continuous on closed interval ab, differentiable on open interval ab, and the functional values are equal, that is f of a is equal to f of b. Then there exists at least one value of x, say c, in open interval a comma b such that f dash of c equal to 0. It is the statement of Rolle's theorem. Geometrical representation of Rolle's theorem. Suppose f from closed interval ab to R be a function satisfying the 3 conditions of Rolle's theorem, then the graph is drawn as follows. So whenever the function is satisfying the three conditions, we can draw the graph. So it is the graph of the curve y is equal to f of x, Cartesian curve diagram in between a and b. These capital A and capital B are functional values at AB, f of A and f of B, and these are at equal distance. Height of these 2 points are equal. That is f of A is equal to f of B. In between these points, we will have x equal to c is a point. At this point, we have drawn a tangent line to the curve, and the tangent line is horizontal to x-axis. That is, the tangent line slope is 0 here. So thus we will have f dash of c value is 0. In second diagram also, which represents the curve y equal to f of x curve, these are endpoints f of a equal to f of b. It is a continuous curve. The functional values are equal here, and the tangent line is horizontal to x-axis. So f dash of c value 0 here. Geometrically, Rolle's theorem means the following: y equal to f of x in continuous curve in closed interval a comma b. There exists a unique tangent line at x equal to c in between a to b. The ordinates f of a and f of b at the endpoints a comma b are equal, so that the points a and b are equidistant from x-axis. By Rolle's theorem, there is at least one point C in between a comma b, the curve at which the tangent line is parallel to the x-axis, and also it parallel to the chord of the curve. So what is the chord here? AB. AB is the chord of the curve. The tangent line is parallel to the x-axis and also parallel to the chord of the curve. So it is the geometrical representation of the curve. In each case, it appears there is at least one point C which belongs to open interval a comma b on the graph where the horizontal, and thus we will have f dash of c is equal to 0. So Rolle's theorem is possible. So look at this graph A. Here clearly in between A and B there is 2 points C1 and C2. So according to Rolle's theorem, one point is more, at least one point must and should be existed. But here we will have 2 points, those are C1 and C2. Clearly at these points, f dash of C value is 0. That is, f dash of C1 is 0 and f dash of C2 is 0. So tangent line is horizontal to x-axis. In second graph, that is a B diagram, here also the tangent line is parallel to x-axis and f dash of c value is 0. It is the curve continuous and differentiable in between AB. So look at this C, the curve as shown in the figure. Clearly we will have two C points, that is C1 and C2. At these points the tangent line is drawn which is parallel to x-axis. So here also f dash of C1 is 0 and f dash of C2 is 0. In last diagram, so we will have D diagram. Here also f dash of C clearly is equal to 0. The tangent line is horizontal to x-axis and f dash of C value is 0. So here also it is the relative maximum. In between A and B we will have the point C and f dash of C value is 0 here. No, Rolle's theorem can be simply represented as a geometrical representation. If 2 points at the same height are connected by a continuously differentiable function, then there has to be at least one place between those 2 points where the derivative or slope is 0. So it is the simple step by understanding the geometrical representation. If 2 points at the same height are connected by a continuous differentiable function, then there has to be at least one place between those 2 points where the derivative or slope is 0. So 2 points means A and B, which are at same height distance. That means f of A and f of B are at the same height distance occurred. And f is continuous function which is also differentiable. Then there is at least one point placed between A and B where the derivative or slope is 0. So it is the simple step by understanding the geometrical representation of Rolle's theorem. Now, applications of Rolle's theorem. Here in applications, we will see some examples. The first example is f of x is x to the power of 4 minus 2x square. Clearly, algebraic expression is given in the interval minus to 2. Clearly, this function is continuous and differentiable because it is algebraic function. Every algebraic function or polynomial in x is a continuous for every x. For example, x lies between in this interval. It is clearly continuous because a polynomial in x is continuous for every x belongs to real number. Here also in this interval also clearly f is continuous. So f of minus 2 is just obtained by replacing x by minus 2 in the given expression. So substituting x equal to minus 2, we will get 8. Now computing f of 2 is also 8. Both the functional values are also equal. At the end points, the functional values are also equal. So f satisfies the three conditions of Rolle's theorem. Hence, by Rolle's theorem, there exists at least one value of x, say c, such that f dash of c is 0. So since Rolle's theorem apply, we will have f dash of x which is equal to 0. What is f dash of x? The derivative of f of x. X power 4 derivative is 4x cube. Negative 2x square derivative is negative 4x. So simplifying this, that is taking out common as 4x. We will have 4x into x square minus 1 which is equated to 0. Clearly, the product is equal to 0. 4 cannot be 0. X is a 0 or x square minus 1 is 0. X equal to 0 and x square minus 1 is a 0, which implies that x square is 1, which implies that x equal to plus or minus 1. Here for x, the three values are existed, and also these 3 points clearly lies in the interval open interval minus 2 comma 2. So Rolle's theorem is strongly verified because all the 3 points are lies in the open interval. So Rolle's theorem is clearly verified. Once again, three conditions are holds good. F is continuous in real number system, but in particular, the F is continuous in this interval. In this open interval also, F is a differentiable because clearly derivative is existed in that open interval minus 2 comma 2. That is except minus 2 comma 2, in between the points minus 2 comma 2, clearly f dash of x is existed. So f dash of x is equated to 0 here, getting x values. All the three values are lies in open interval minus 2 comma 2. It is enough to one value is existed in open interval minus 2 comma 2. But here all the 3 points are lies in open interval minus 2 comma 2. Hence Rolle's theorem is strongly verified. Another application of Rolle's theorem, f of x is a mod x. Clearly it is the definition of modulus of x on closed interval minus 1, 1. Clearly f is a continuous in the interval minus 1 comma 1. We can draw the diagram also. The graph function of over the interval on your calculator. We can clearly define the graph of the this curve, that is f of x curve, that is modulus of a function. Now continuous on closed interval minus 1. But f of x is not differentiable at 0 because the derivative does not exist at the point x equal to 0, because left hand derivative and right hand derivative existed but both are not equal. What is the formula for left hand derivative? Limit x tends to 0 minus f of x minus f of 0 by x minus 0. Right hand derivative at x equal to 0 is limit x tends to 0 plus f of x minus f of 0 by f of x minus 0. Both the derivatives, left hand derivative, right hand derivative are existed, but both are not equal, so that the function derivative is not existed at the point x equal to 0. So second condition of Rolle's theorem is clearly not existed. So that means f is not derivable at the point 0 in the interval minus 1 comma 1. It concludes that not differentiable at minus 1 comma 1 open interval minus 1 comma 1. So f of minus 1 is equal to f of 1, but Rolle's theorem does not apply since the second condition of the Rolle's theorem is not holds good. The second condition fails here, so f is not differentiable in open interval minus 1 comma 1. The Rolle's theorem cannot be applicable, so Rolle's theorem does not apply. Another application of Rolle's theorem: given function is f of x is sin x upon e power x or e power minus x sin x in closed interval 0 comma pi. So given function is clearly continuous because sin x is continuous and e power x is also continuous. So sin x into e power x is also continuous, or sin x into e power minus x is also continuous. If f and g are continuous, then f by g is also continuous. And also the denominator function. What is here the denominator function? Exponential function, which is clearly not equal to 0. So we will have a known theorem, that is, if f is continuous and g is continuous and g of x is not equal to 0 for all x in the given interval, then f by g is also continuous. So sin x continuous, e power x continuous. Sin x by e power x is also continuous because e power x is not equal to 0 in the given interval. That is, exponential function cannot be 0. So sin x by e power x is a continuous function in the closed interval 0 comma pi. So since sin x and e power x both are differentiable in the interval 0 comma pi. What is the derivative of sin x? Cos x, which is existed in open interval 0 comma pi. E power x derivative is as it is e power x, which is also defined in the open interval 0 comma pi. So f is derivable in open interval 0 comma pi, and we will have the endpoints functional values, that is f of 0, which is obtained just by replacing x equal to 0 in f of x, that is a sin 0 upon e power 0. Sin 0 0, e power 0 1, 0 by 1 0, f of pi sin pi by e power pi. But what is the sin pi? 0, 0 upon e power pi. 0 by any number or 0 by any variable function is clearly 0. So thus we will have f of 0 is equal to f of pi. That means both the functional values are equal. Since f satisfying all the three conditions of Rolle's theorem, f satisfying these three conditions, so there exists a point C belongs to open interval 0 comma pi such that f dash of C is 0. Now f dash of x, what is f dash of x? Which is obtained just by differentiating f of x with respect to x, which is obtained by using division rule, that is u by v formula. What is the derivative of u by v? V u prime minus u v prime whole upon by v square, where v cannot be 0. What is u here? Sin x. V power x is v. U by v derivative is vu dash minus uv dash whole by v square. V is e power x here, clearly exponential function not equal to 0. So such that we can compute the derivative. Thus we will have e power x kept silent. Sin x derivative is cos x minus sin x kept silent. E power x derivative is as it is e power x by v square. V square means e power x whole square. Now taking the common as e power x, clearly one of e power x get cancelled, so that we will have f dash of x is cos x minus sin x by e power x. It is f dash of x, but by Rolle's theorem there exists at least one value of x, say c, such that f dash of c is equal to 0. Just replacing x as c and f dash of c is equated to 0. That is cos c minus sin c upon by e power c equal to 0, which implies that e power c on cross multiplying we will have 0 into e power c is 0. Thus cos c minus sin c is 0. Cos c is equal to sin c. So dividing with cos c, we will have sin c upon cos c is tan c. Tan c is equal to 1. Thus we will have c is pi by 4 because 1 is replaced with tan pi by 4. Now taking tan inverse on both sides, so we will have c value is pi by 4, clearly which belongs to open interval 0 comma pi. Hence the Rolle's theorem is verified. So simple thing once again. So verify Rolle's theorem. Since sin x and e power x both are continuous in closed interval 0 comma pi, therefore sin x by e power x is also continuous in an interval. Sin x and e power x are derivable in open interval 0 comma pi. F is also derivable in open interval 0 comma pi. Clearly, the derivative of f of x is existed in the open interval 0 comma pi. Also, we will have the functional values. F of 0 is sin 0 by e power 0, that is a 0. And f of pi is sin pi by e power pi. But sin pi value 0. 0 by e power pi is 0. So both the functional values are equal. Thus, f satisfying all the three conditions of Rolle's theorem are satisfied. By Rolle's theorem, there exists c which belongs to open interval 0 comma pi such that f dash of c is 0. Already we will have f dash of x. To get f dash of c, just we have to replace x as c in f dash of x. Thus f dash of c is equated to 0. Cos c minus sin c by e power c is equated to 0. On cross multiplying we will have cos c is equal to sin c. Dividing with cos c we will have cos c by cos c is 1. Sin c by cos c is tan c. Tan c equal to 1, which implies that c is pi by 4 because 1 can be taken as tan pi by 4. Applying tan inverse on both sides, we will have c is a pi by 4. Clearly c value belongs to open interval 0 comma pi. Hence the Rolle's theorem is clear. Another application of Rolle's theorem. Example. Verify whether the Rolle's theorem can be applied to the following functions in the intervals. Given function is tan x. Interval is 0 pi. And second one is f of x is 1 by x square in the interval minus 1 comma 1. For first function, clearly which is the discontinuous at the point x equal to pi by 2, because the function is not defined there. What is the value of tan pi by 2? Infinity, undefined. So f of x is not continuous at the point x equal to pi by 2. Not continuous means discontinuous at the point x equal to pi by 2. Thus the condition 1 of Rolle's theorem is not satisfied. Hence we can't apply Rolle's theorem here. So Rolle's theorem cannot be applicable for the function f of x is a tan x in the interval 0 comma pi, because the first condition of Rolle's theorem is not satisfied. What is first condition? F of x must and should be continuous in the given closed interval 0 comma pi. Here f of x is not continuous at a particular point pi by 2. So f of x is discontinuous at the point pi by 2. So Rolle's theorem cannot be applied. For second function, what is the function here? 1 by x square, which is discontinuous at the point x equal to 0. What is the value of 1 by 0 square? That is 1 by 0, but 1 by 0 value is undefined. So f is discontinuous at the point x equal to 0, thus Rolle's theorem cannot be applicable. Another example, using Rolle's theorem, show that g of x is 8x cubed minus 6x square minus 2x plus 1 has 0 between 0 and 1. So clearly given function which is a continuous and differentiable because it is a polynomial or algebraic expression. And also g of 0 value, g of 1 value, which is obtained by replacing x as a 0, and which is obtained by g of 1 is obtained by replacing x as 1. Both the values are equal. So all the three conditions of Rolle's theorem are clearly satisfied. Hence, by Rolle's theorem, there exists a value c which belongs to open interval 0, comma 1 such that g dash of c is equal to 0. Here the function just is named as g. Generally, we will use f. Here in this problem, g is used. So g dash of x value which is obtained by derivative of g of x with respect to x. X cube derivative 3x square, already we have 8, that is 24x square. Negative 6x square derivative is negative 12x. Negative 2x derivative is negative 2. And one derivative is a constant whose derivative is 0. So g dash of x value, now g dash of c is equated to 0. G dash of c which is obtained by x is replaced with c. So g dash of c is equated to 0, and solving this equation we will get c value. So c values are two occurred here. One is a 0.63 and another one is negative 0.132. But here c value, only one c value is lies in open interval 0, 1. So minus negative 0.312 does not lies in open interval 0, comma 1. Only one value is lies in open interval 0, comma 1. Thus, there exists at least one root which lies between open interval 0, comma 1. Hence, the Rolle's theorem is clearly verified. So once again, given g of x, clearly continuous, differentiable, both the functional values are equal, Rolle's theorem three conditions are satisfied. Already we have computed g dash of x and g dash of c is equated to 0. Solving quadratic equation, we know that the quadratic equation roots are c equal to minus b plus or minus root of b square minus 4ac by 2a. What is a here? 24. What is b here? Negative 12. What is c here? Minus 2. So getting the two roots obtained for quadratic equation. So here the quadratic in c here. So c roots are c equal to minus b plus or minus root of b square minus 4ac by 2a. Using the formula, we will get c values. But here only one value lies in the open interval. So by Rolle's theorem, there exists at least one value which lies in given open interval a comma. Hence, Rolle's theorem is verified. So another example, verify Rolle's theorem for the function x into x plus 3 into e power minus x by 2 in the closed interval minus 3 comma 0. Clearly given expression having two functions, one is algebraic or polynomial and another one is exponential. So clearly both are continuous functions. Every algebraic or polynomial is continuous for all values of x, and exponential function is continuous for all values of x. If f is continuous and g is continuous, then the product fg is also continuous. So here both are continuous functions. The product is also continuous for all values of x. In particular, f and g, that is the product is continuous in the interval minus 3, 0. So both are continuous function. So the product is also continuous for every x, that is for every real number it is continuous. In particular, in the given interval also both the functions are continuous. Hence the product is continuous in the interval minus 3 comma 0. Now we will have f dash of x. The product, the f dash of x, the derivative which is obtained by using the product rule. So product rule is u v dash plus v u dash. That is x into x plus 3 kept as a silent. e power minus x by 2 derivative is e power minus x by 2, and then minus x by 2 derivative is minus 1 by 2. Now e power minus x by 2 is kept as a silent. Now derivative of x square plus 3x derivative. X square derivative is 2x. 3x derivative is 3. So the derivative is obtained by using product rule, that is UV rule. What is UV rule? UV dash plus VU dash. U kept silent, the derivative of V is V dash. V kept silent, the derivative of U is U dash. So like this, we have to compute the derivative of the function, that is f of x derivative is f dash of x. Now taking out the common as e power minus x by 2 in two terms. So we will have e power minus x by 2 into 6 plus x minus x square by 2 by taking the LCM as 2 here, that is 4x plus 6 minus x square minus 3x square, rewriting the terms. So we will have 4x minus 3x is x, negative x square, and 6. So constant is 6 whole upon 2. Since f dash of x does not become infinite or indeterminate at any point of the interval, open interval minus 3 comma 0. So clearly f dash of x is existed in the given open interval minus 3 comma 0. So f of x is clearly derivable. Thus the second condition is also verified. Now third condition. So also we will have f of minus 3 value is 0 and f of 0 value is 0. Both the functional values are equal. So thus f satisfies all the three conditions of Rolle's theorem in the interval, closed interval minus 3 comma 0. Hence by Rolle's theorem there exists at least one value, that is a c of x, in the interval minus 3 comma 0, such that f dash of c is 0. Already we have computed f dash of x here. So here in this f dash of x, just we have to replace x as c. So to get f dash of c. So f dash of c is equated to 0, and computing the c value. So c value computed here using quadratic equation roots. So quadratic equation C is the equation here, which is compared with AC square plus BC plus C. What is A here? Negative, or A is 1, B is 1, C is minus 6. Or computing like this, the product form linear product, the quadratic expression can be written as the product of two linear expressions. Or we can find by using the roots c equal to minus b plus or minus root of b square minus 4ac by 2a. Using the formula also we can derive the c, the equation satisfying c values, or equation satisfying zeros. That is the c values are here, two values are occurred, that is one is the 3 and another one is minus 2. So clearly the value of c minus 2 lies within the open interval minus 3 0, which verifies the Rolle's theorem. So easy thing, just the two functions are continuous, the product is also continuous in the closed interval minus 3 0. The derivative is clearly existed here in for every value of x in open interval minus 3 0. So f of x is derivable, because f dash of x is existed. The second condition is also satisfied. Also we have the functional values at the end points, that is f of minus 3 is a 0 and f of 0 is also 0, which is obtained by replacing x equal to minus 3 in the given function and x equal to 0 in the given function. Both the functional values are equal here. Thus f satisfies the three conditions. By Rolle's theorem there exists one value for x, say c, which lies in open interval minus 3 comma 0, such that f dash of c is equated to 0. Computing c values, we will have the two values are here, c equal to 3 and c equal to minus 2. C equal to 3 clearly does not lies in open interval minus 3 comma 0, but c equal to minus 2 clearly lies in minus open interval minus 3 comma 0. Hence the Rolle's theorem is verified. Another example, f of x is x minus a whole power m into x minus b whole power n in closed interval a comma b. Clearly, f is continuous. F dash of x is obtained by using product rule, and we will have the functional values at the endpoints. F of a is a minus a whole power m, that is a 0 into any function 0. F of b is also b minus b, 0 0 into any function 0. So thus we will have the three conditions of Rolle's theorem are clearly satisfied. Hence by Rolle's theorem there exists one value for x, say c, in open interval a comma b, such that f dash of c is equated to 0. So f dash of c is equated to 0, which implies just replacing x as a c here and computing for c values, the product is equal to 0. The expression c minus a whole power m minus 1 is equal to 0, or c minus b whole power n minus 1 equal to 0, or m plus n into c minus of na plus mb equal to 0. Now computing these three values, we will have three values for c, but c equal to a and b are the endpoints. Both are does not existed in open interval a comma b, but the value c equal to mb plus na by m plus na m plus n, clearly the value lies in the open interval a comma b. If we take example, if we take mn as 1 comma 1, so clearly we will have a plus b by 2, that is the arithmetic mean of a and b, clearly lies in open interval a comma b. Thus we can generally say that mb plus na by m plus n is also lies in open interval a comma b. So thus the Rolle's theorem is clearly verified. Here mn are positive integers. We have to take only positive integers, that is m greater than 1 and n greater than 1. Then only c values existed in open interval ab. Thus the Rolle's theorem is clearly verified. So simple thing, just f of x, take f of x, compute f dash of x. Clearly fx is the product of polynomials in x. So clearly f is continuous, which is also differentiable, and the functional values are coincide here. So by Rolle's theorem, we will have f dash of c is equal to 0. F dash of c is equated to 0. Thus we will have three values per c, but first two values are does not existed in the open interval a comma b, because ABs are endpoints here. The last value of C clearly lies. For example, if we take M as a 2 or M as a 3, clearly the value is existed here. So MB plus NA by M plus N is clearly lies in the open interval AB. Thus, the Rolle's theorem is verified because at least one value of X lies in open interval AB. So clearly Rolle's theorem is verified. Another application, that is verify Rolle's theorem for the function log of x square plus ab by x into a plus b. So same log of a by b is log a minus log b. Log function is always continuous. Log x is continuous for x greater than 1. Both the functions are continuous here. F is continuous, g is continuous, then f minus g is also continuous. Like that, f is a composite function of continuous functions in closed interval a comma b. It is a continuous in closed interval a b. Thus f is continuous, g is continuous, then f minus g is also continuous. The composite function of continuous function is always continuous. Now f dash of x, just what derivative of f of x with respect to x. Log of x square plus ab derivative is 1 by x square plus ab, and then x square plus ab derivative is 2x. X square derivative 2x, ab derivative is 0. Now log x derivative is 1 by x. Now log of a plus b derivative is a constant whose derivative is 0. So negative 1 by x minus x square minus ab by x into x square plus ab, which is obtained by taking the LCM of two terms. So which is equal to like this, that is x square minus ab by x into x square plus ab. Clearly f dash of x is existed for every x in open interval a comma b. So we will have f of x is derivable in open interval a comma b. Thus f satisfying all the two conditions of Rolle's theorem. And last one is the functional values at a and b. F of a, which is obtained by just by replacing x equal to a, that is log of a square plus ab by a into a plus b. That is a into a plus b is a square plus ab. Clearly a square plus ab, a square plus ab get cancelled. We will have log 1. But what is the value of log 1? 0. So similarly, f of b is also 0. Both the functional values are also equal. Thus, f satisfying all the three conditions of Rolle's theorem. Hence, by Rolle's theorem, there exists at least one value for x. Simply say it as c, which lies in open interval a comma b, such that f dash of c equal to 0. So f dash of c is equated to 0 here. So that c square minus ab by c into c square plus ab, which is equated to 0. And taking cross multiplication, we will have c square minus ab is a 0, which implies c square equal to ab. Thus, for c values, 2 existed here, that is plus or minus root of ab. But clearly plus root of ab is existed, lies in open interval a comma b. Hence, the Rolle's theorem is clearly verified. So simple, just f is continuous, f dash of x is obtained, f dash of x is existed for all x belongs to open interval AB. That means f of x is derivable here, and also the functional values are coincide here. By Rolle's theorem, there exists one value for x, say c, such that f dash of c is 0 here, f dash of c is equated to 0. Thus, we will have c equal to root of AB, clearly which lies in open interval a comma b, because root of AB is the geometric mean of A and B clearly lies in open interval A comma B. Hence, the Rolle's theorem is clearly verified. Thank you. For any queries, contact mobile number, and this one is my mail address.